Math with Oscar class. That's my dad.
Alright, as we move into 1-2, we have a couple of bits of vocab to pick up before we get to the big idea, which is the segment addition postulate. That's coming up. Before we do that, we need to establish definitions for distance, for length, and for congruent segments. Now when I talk about distance, the textbook definition of this refers to the absolute value of the difference of the coordinates. Now, that's a very long way of getting to a very simple idea. That is, if I have a number line, here's 0 on my number line. Here's -1, 1, 2, 3, 4, and 5. And on my number line, I have a point, let's say here at 1, and a point here at 4. Then the distance between 4 and 1 is the absolute value of 4 minus 1, which is the absolute value of 3, which is simply 3. So the distance from 1 to 4, or the distance between A and B, would simply be 3. Now likewise, I might talk about C. So say I want to do the distance between C and B. Alright, that's going to be the absolute value of -1 minus 4, which would be the, let's trim that 1 up so you can see the absolute value of -1 minus 4, which will be the absolute value of -5, which is simply the value 5. So in this case, the distance between C and B would be 5 units. When I talk about the length of a segment, I'm talking about the distance between the endpoints. Now, length only has meaning when we talk about segments. It's not going to have meaning when we talk about rays or lines, because those are infinite. They go on forever. So if I were to talk about this segment right here, call it the segment PQ. So this thing is the segment PQ. That's the thing. The length of the segment will be some number. Say the number is 5. Meaning that there are 5 units between P and Q. It's also important to note there's no bar over the Q. See, there's nothing here. This tells me it's a segment. This tells me it's a length. This is a thing I can draw, the segment PQ. This is a number I can measure and work with. So, no bar, number, bar, segment. Now when I talk about congruent segments, what I'm talking about are 2 segments with the same length. Congruent segments. 2 segments with the same length. Now, here's the segment. We'll call it XY. Here's a segment. We'll call it WZ. If they have the same length, I can say they are congruent. Now, how would I write that? So when I want to talk about writing out 2 segments that are congruent, I would write bar XY. This symbol means congruent. WZ. This says that segment XY is congruent to segment WZ. If I write this, XY equals WZ, I'm saying that the length of XY is equal to the length of WZ, or the two numbers are equal to each other. Let's be clear. Things are congruent, numbers are equal. So congruent, things, equal sign with a squiggle, equal measures, number, no bar, kind of like we did over here where we said the length of PQ is 5. That's what I'm doing over here. And I can then set these guys equal to each other because congruent segments have the same length. The big idea in 1.2 is the segment addition postulate. It's the big overlap between geometry and algebra, and it ties in with what we worked on in class relating to the hurdle problem. What it says is this. If B is between A and C on a line, then AB plus BC equals AC. Now that probably seems a little odd without some context, so let's draw what it's describing. There's A, there's C, they're on a line together. Here's B, situated between A and C. What this says is that this part here plus this part here is equal to that part there. Let's put some numbers on for context. Let's say I told you that this distance along here, the length of AB. Now notice I wrote AB without a bar. That means it's a number. Is equal to 3. And BC is equal to 5. Well, how long is it from A to C? If it's 3 from here to here and 5 from here to here, then the whole thing must be 8. That's the length of AC. That property that you're using is called the segment addition postulate. Some textbooks call it the part and whole principle, or something along those lines, because again, we're taking two parts, this part, and we're combining them to create a whole. Same idea here. Now where we're going to be using this mostly is algebraically. So again, what if we take some of our concrete numbers out? If I were to tell you that this part I don't know, call it x. This part I do know, let's call it 6. And the whole thing, AC, is given as 8. We'll stick with 8 as a good number. Can I write an equation that will tell me how to find x? Follow the parts and whole. Part plus part equals the whole thing. So in this case, following this rule, AB plus BC equals AC. Therefore, x plus 6 equals 8. Now it's an algebra problem to solve, and not even too bad a one at that. I know many of us will look at this as a subtraction problem. 8 take away 6 is going to leave me some amount. And that will work for the simpler problems. Where you're going to run into trouble is when everything up here is based on variables. So you want to be watching out for that. As we get into the example problems, you'll see more and more of those. We'll pick those up after the break.